Welcome to the Geometry 6.0 notes. We're going to be looking at two main topics on this video. The first one is we're going to look at how to solve proportions. And then the second topic that we're going to look at is more with simplifying radicals, which we've done some of this already this year, but we need to extend this just a little bit. So starting with solving a proportion is an equation where two or more fractions or ratios are equal to each other. Something like this, 1/2 is equal to 3/6. Those both actually have the same value, or is equal to 4/8. This is a proportion. You can have two fractions, but you could have more than that. We could actually have a whole bunch of them if we wanted to. Now, when we solve a proportion, we're solving for x. Here's an example. Let's say we have something like this. X over 10 is equal to 3 over 9. Oh, I'll do 3 over 8. A lot of times these answers will be decimals. Don't stress if that happens. It doesn't mean you did the problem wrong. We're trying to find out what value of x would make these two fractions equal to each other. The strategy that most people use is called cross multiplying. I spelled it wrong. Goodness sakes, sorry. The strategy, there we go, that most people are using is called cross multiplying. To cross multiply, what you're going to do is you're going to look at the terms that are diagonal and you're going to multiply them. And you want to make sure that you set them equal to each other. Notice this is a new equation with no more fractions in it, and then you can just solve this equation by dividing. If you want, you can make this a fraction. If I divide by 2, this would be 15 over 4, or I could make this a decimal, 3.75. Now, they can have some where when you solve proportions, you can have a little more complicated equations, because you could have something like this. X plus 3 over 5 is equal to x minus 2 over 7. I'm still going to use the strategy of cross multiplying. What I'm going to do is multiply the 7 by the x plus 3. Now, because the x plus 3 has two terms, please notice that I'm putting in parentheses here. The 7 is going to need to distribute to both of those terms. I'm also going to multiply the 5 to the x minus 2. Note the parentheses. This is because of the distributive property. And you set those equal to each other. I'm going to distribute on both sides. Make sure when you're distributing that you're multiplying. Since my x terms are on two different sides, I'm going to cancel one set of these. You can pick which one. And then I have an easier equation to solve. So I'll just use inverse operations to solve this equation from here. And again, if you want, you can write your answer as a fraction. This one does not reduce. Or you could make this a decimal, whatever you'd prefer. Okay, so that's one topic that you're going to see on the homework. The other topic is we're going to be simplifying radicals. Radicals, the most common type of radicals are square roots. You might remember that we've done these before with factor trees, and we put pairs on the outside, and then any leftover factors we put on the inside. And so here's our first example. I'll call this example 3. We'll just kind of count on from the previous topic. If I wanted to simplify the square root, perhaps of, let's say, 48, I can go ahead and break this down into some factors. Now, there's more than one way that this factor tree could look, but what you want to make sure is that you're breaking these down into prime factors. It's a good strategy. Anytime you have a pair, pairs will go on the outside. If you have more than one pair, they get multiplied together. This leftover factor of 3 will stay on the inside, and my answer is 4 root 3. Please notice I did not use these numbers anymore. They're not actually there anymore. I broke them down into smaller factors. So I'm using the 2, the 2, the 2, and the 3 to get my final answer. Sometimes you'll have some of these where you're going to see a fraction in with them. And you might see perfect squares, something like this, the square root of 16/25. Well, what you can do is you can just recognize that both the numerator and the denominator need to be square rooted. We're still looking for pairs. Now you might recognize right away that 16 is a perfect square. It's a pair of 4s. Notice that because this is a perfect square, there is no square root symbol anymore. There's no leftover factors. So there's nothing left for that. We don't write it. The square root of 25 is 5 because 5 times itself is equal to 25. There are times when you're doing these with the fractions that you might have to fraction reduce first. You might see something like this, the square root of, let's do 18 divided by the square root of 98. Well, by the way, these are not perfect squares. But if you reduce these fractions by the common factor of 2, then I'd get the square root of 9 over the square root of 49. These are now both perfect squares, and I'll get 3 over 7. The last type is we are not allowed to have a square root on the denominator of an answer. So for our final answer, if we can't get a whole number here, then we have to use a specific process called rationalizing. When you rationalize, what you do is you multiply by a useful form of 1 to create pairs. You want to create pairs or perfect squares. Here's an example. Let's say of something like this. 1 divided by the square root of 3. Well, I can't do any fraction reducing here. One of these is a whole number and one of them is a square root. I also don't have any pairs for a factor tree here. So I can't simplify this. So what I'm going to do is I'm going to rationalize. I'm going to multiply this by a useful form of 1. Well, the form of 1 I'm going to choose. 1 can be formed by having anytime you have the same number on the top and the bottom. That's 1. Here, this is also 1. Those just aren't useful forms in this problem. Here's a useful form of 1. I'm going to multiply this by root 3 over root 3. I chose that because I wanted to duplicate what was already on the denominator. The reason I'm doing that is because then when I multiply straight across, this 1 stays on the outside. I would get 1 square root 3 over root 3 times root 3 is root 9. Well, what is the square root of 9? The square root of 9 is whole number 3. This is a pair right here. This is a pair. This forms a perfect square. Notice that I no longer have a square root on the denominator, so this is a good answer. Writing the 1 is optional. Sometimes you might have something like this, 3 over the square root of 7. I cannot simplify this. I cannot fraction reduce. There are no factors here to form a factor tree. So I'm going to multiply by root 7 over root 7, which is a form of 1. This is called rationalizing. On the top, the 3 is on the outside. It stays on the outside. That would be 3 root 7. On the bottom, this forms a pair. This is whole number 7. Last one. Let's say I have something like this. 4 over the square root of 2. I cannot fraction reduce these because one of these is a whole number and one's a square root. They're not the same type of numbers. I also cannot make a factor tree because 2 is prime. So I'm going to rationalize this by root 2 over root 2. On the top, I'll get 4 root 2. On the bottom, this is a pair, so I'll get whole number 2. These whole numbers now can reduce down. 4 divided by 2 for the whole numbers is 2, and that root 2 is still there. This is the end of the video for the 6.0 notes.